All right. Um. So this year our first topic is module 1, and we're going to start dealing with carbon to carbon chemistry and carbon to carbon compounds, which will be under organic chemistry. So what is carbon? As you remember, carbon is a tetravalent element, and by tetravalent we mean that it has 4 electrons in its outer shell, which are available for the formation of covalent bonds. So here in my methane that I have here, I have 1 carbon and it is bonded to 4 hydrogens, and each arrow points out the hydrogens, as we could see. And so yeah, so we see that it has the ability to form 4 different bonds. All right, so carbon is quite a phenomenal element, in that it has so much things that it can do that makes it so good. One of the things that makes carbon phenomenal and so good is the fact that it can perform catenation. Now, catenation is when C to C bonds form long chains. Okay, so carbon can form bonds with itself, and these C to C bonds are so strong when we compare them to other bonds. So in the study guide, when we see carbon to carbon bonds, we see that the study guide has it broken down, and they show the bond dissociation of each bond: carbon to carbon, oxygen to oxygen, nitrogen to nitrogen. And carbon has the highest bond energy, and it takes so much energy to just break a carbon to carbon bond, hence why we are looking at them. Alright, so they have this ability to form long chains with each other. And so we have here pentane, which is essentially 5 carbons bonded together with hydrogens bonded around them. Now I want you to note that each carbon has 4 bonds to it. In any point of carbon to carbon chemistry or carbon compound chemistry or any form of chemistry relating to carbon, and you're drawing out your structures, please make sure that your carbon has 4 bonds. Never 5, never 6, 4 bonds. So we see here, if you could see my mouse. Alright, if you see my mouse, I just made it. Wait, oh, laser point. If you can see the laser point, 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds, and 1, 2, 3, 4 bonds. So each carbon has 4 bonds. And here, even in our ring structure, we see that this C has 1, 2, 3, 4 bonds. Okay, so it's never a case that your carbon will have any more than 4 bonds, and if it has a positive sign, it has 3 bonds, but you won't see that. So when you're drawing out your ring structures, your straight chains, or anything like that, we're going to start from now. We're just going to make sure that all of our carbons have 4 bonds. Okay, so carbon has a next special ability, and that is hybridization. Carbon has the special ability to rearrange its electrons. This process is called hybridization, and in this process, an electron from the 2s shell is promoted to the 2p3, allowing for carbon to have 4 valence electrons. Okay, alright, so if we'll remember, this would be our representation that we have gone through last year. So we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 2 electrons in the 2p3 orbital shell. Okay, so we see that this electron is then pushed through energy and is brought up, kind of upgraded to become this lone pair electron. So here we see that carbon has 2 valence electrons. I'm sorry, this is going to look really horrible because I'm writing on my iPad, on my tablet. And so here we see that it now has 1, 2, 3, 4 valence electrons. So that's basically it. Alright, so this hybridization process goes into kind of a fancy thing where we get mixing. Alright, the hybridization orbitals of carbons have the ability to mix and create their new orbitals, but note that these new orbitals that are created must be of equal energy. Alright, so this allows carbon the opportunity and to have the ability to form single, double, and triple bonds with itself. Alright, so our mixing, if you have a 2s plus all 3 of your 2p3s of your 2p orbitals, you form an sp3 orbital, which allows carbon to have 4 single bonds. Alright, I hope everyone's getting me. If you're not getting me or you're not understanding, you can just pause me or anything like that if I'm going too fast, you know. Alright, so we see how our boxes are highlighted here. Alright, so if you have a 2s orbital plus 2, not 3, 2 2p orbitals, we get a mix which produces an sp2 orbital where carbon can form a double bond. Now when we have a sp2 orbital, we have 3 atomic orbitals which are mixing, leaving 1 pure p orbital. So you will have your sp2 orbital, which will be your 2s, your 2p's, and then you will have 1 2p missing, and that will be your pure p orbital. Alright, and you will have a sp2 hybridization, which gives way to double bonds. Alright, if a 2s orbital and a 2p orbital are mixed, an sp orbital is formed, and that gives rise to triple bonds. So we'll see that we have right here our sp orbital, and then we'll see that we have now 2 pure and unmixed p orbitals. Alright, so this results in a triple bond. I really do hope that everyone is understanding. I'm going to take the silence as go ahead ma'am, go ahead Shanice, and go on. Alright, so resonance. For resonance, we see that we have delocalized electrons. Now, what is delocalized electrons and what are localized electrons? So localized electrons basically refer to when we confine the electrons in a fixed place. So when you have a straight bond, a straight ring, you see that you know where your electrons are around your carbon. However, within benzene, as we see down here, there is kind of an overlap of the rings, so of the orbitals. So there's an orbital here, a sp orbital, an sp orbital here, and an sp orbital here, and they overlap within, and they provide within the molecule and provide a way that, let me erase that so it doesn't look too crumpy. So I provide a way that electrons can move throughout the molecule, so there's no particular place movement of the electrons within that molecule. So as we can read here, resonance occurs when electrons become delocalized, i.e. the molecular orbitals extend over one another and allow for the free movement of the atoms. This occurs in benzene, where there are 3 sp2 bonds present and they overlap, and this allows for the free movement of electrons within the ring. So benzene can be drawn like this, can be drawn like this, or it can be drawn like this. There are 3 ways you can represent it. I prefer, if as we are starting now, that you use this way and show all of your carbon to carbon bonds with your hydrogen and we move. Okay, so this brings us to homologous series. So what is a homologous series? A homologous series is a group of organic compounds, so carbon to carbon compounds, which have the same functional group and can be placed in well-defined groups. And what do we mean by well-defined groups? Well, they have certain properties that allow them to be defined as a part of that group. So what are these properties? The properties of the homologous series are: 1, that they all have the same general formula, i.e. there is a set relation between the number of different atoms in the compound of the homologous series. For example, alkanes. Alkanes have a formula of CnH2n. Therefore, if you have an alkane, with 1 carbon, you will have C, and then you will have H times 1, so you will have CH2. If you have an alkane that has 2 carbons, you will have C, your N will be 2, alright, and it will be H, and then it will be 2 times 2, which will be 4. And the same thing goes for if you have a carbon with 3, so C3, H, and 6. Alright, and so that is how we go, and it goes on and on and on and on down to probably infinity, if we can. So if we have infinity, C infinity, it will C infinity times 2 infinity. Each successive member increases by a mass of CH2, which will be a mass of 14. So we see we have 1 C, and so we see if we have a CH, and if we have right here, if we have plus CH2, we will get this, because we will have 2 carbons and 4 hydrogens. Alright, and so if we have this and we go plus CH2, we will have this. So our 2 carbons were combined with that 1 C3, and H4 will be 4 plus 2, which will be 6. They all have a functional group. Now in some, the functional groups are very defined and can be seen. So in alcohols, you will have a functional group of OH. In carboxylic acids, you will have a functional group of COOH. Everyone's in fast in the pain, so and so that's what we're seeing here. Alright, so we will see functional groups, and we will see, so for example, where we have alkenes, our functional group will be the C single bond C with our H's. So as you continuously, if you see a straight line of C to C carbons, that will be alkenes. Alright, they all have similar chemical properties. Now our chemical properties, let me just erase so that the slide looks less. So our chemical properties will be changing as we go ahead. Our chemical properties and our chemical properties will be defined by the bonds that they partake in and everything. So if you have a group, you will see that alcohols more than likely will react the same way. Once they're all primary or once they're all secondary alcohols, they'll react the same way. Alkanes will all react the same way. The product will be different depending on the amount of carbons that they have in it. However, if you add an alcohol plus a specific substance, you will have, if you add an alkane plus a specific chemical, you will probably produce the same thing. However, the number of carbons will differ depending on the number of carbons that you started with. Now, physical properties of the compound are determined by the number of carbons in the atom. Our physical properties will refer to things like melting point, boiling point, and stuff like that. So we will see that as you add carbons, that you get a larger molecule. Therefore, breaking down these molecules and boiling them or melting them or freezing them, stuff like that, will generally increase as you increase with carbons. So it differs sometimes depending, and we'll get into that more. So here we have our table, and this table just listed reverse, right? This table just lists off some of the homologous series that we will be seeing here in our Unit 2 chemistry. We see their alkanes, the general formula. They don't particularly have a functional group, and we see some examples along with their actual formula there. The same for alkenes, the same for alcohol, and the same for carboxylic acids. Alright, I'm seeing no messages, so I'm hoping that everyone is good so far. A formula that gives this. Alright, so then we go on to our empirical formulas. So we're going to do some questions with this. So what is an empirical formula? An empirical formula is a formula that gives the simplest whole number ratio or ration of atoms in a compound, and that is referred to as the empirical formula. So how do we calculate our empirical formula? We start with the number of grams of each element given in the question. Alright, now some questions will give you the number, will give you a percentage. In that case, we determine that the mass of the compound is 100 grams. Therefore, since a percentage is of a number of 100, the percentage of the compound that we have, or the element that we have, will then equal to the mass of the element. So if you are given, so in this case, if you are given 37% of Cl, we will assume that the mass is 100 and the mass of the Cl will be 37 grams. Really, I'm hoping that everyone is understanding. We'll look at some questions after. Yeah. And then after that, you convert the mass of each element to moles using the molar mass from the table. Alright. Now, I know everybody dislikes moles, hates moles, can't stand moles, but the molar mass from the table is grams divided by moles. Okay? So if you have the mass of your element and you have grams divided by moles, you're going to want to cancel out the grams. Alright? So you're going to divide the mass of your element. I'm so sorry. I really do hope y'all can understand. And you're going to divide it by your molar mass. So that would be your, I'm just going to put RM. And since this is grams per mole, and this is grams, this will cancel out, and this will move up and become moles. I really do hope everybody's understanding that. So that will be your calculation, and then you will have more than likely you will have more than one, and so then you would have each mole, and you will divide the number of moles by the smallest number of moles that you have calculated. So for example, if we have Cl and we have H, and what we worked out for Cl was, let's say, 6, and what we worked out for H was 2, we will then use the 2 moles that we calculated for H and divide that by 2, which will give us 1, and we will divide this by 2, which will give us 3. Alright, or for example, what if we had gotten 5? Alright, we will then have 2.5. In this case, we round off to the nearest whole number, so this 2.5 will then equal to 3. Alright, and so we will go through our next definition and some other stuff, and then we'll go through a question that we work out the empirical formula of the element. Alright, and so molecular formula. A molecular formula shows that the actual number of atoms, a molecular formula shows that the number of atoms in each element. So if we have, one minute, we can't put that right. So if we have, for example, HCl, that will be our molecular formula. Yes, JSL we will be having class every Sunday 6 to 7. Or for example, we have used benzene, C6H6. That will be our molecular formula. This is because this is actually how much is in our benzene ring and how much is in our molecule altogether. So for example, if we have methane, we have CH and 4, and that will be our molecular formula. Alright, so I'm just going to ask it. And I am going to stop sharing, and I am going to come and join from my iPad. I hope everyone can still hear me. Can everyone still hear me? Can everyone still?
Yes,
okay. 1 minute. I just looking to see how to do it on my iPad. So I'm joining from my iPad. Alright. Can y'all see that I'm broadcasting from here, from my iPad? Y'all can see what's happening on my iPad. I really do hope you can. Let me see. Oh, y'all. Oh, all right. I'm figuring out what's happening. Alright. So what's gonna happen is I have to join from here. Alright, so from what I can see, everyone can see my iPad, and so I'm going to show you the question that I have. So the question that I have states that, and this is from a textbook,